My name is Jim, and today's topic is Thevenin equivalent circuits. And this is another circuit analysis tool we need to learn about that will help us solve network problems. It is good from the standpoint of being able to simplify a source, and it can also be used in AC circuits with complex numbers. And the restriction is there can only be one source in it. If there's more than one voltage and or current source, then we have to resort to other tools like mesh analysis or nodal analysis. It's abbreviated TEC. So this is my circuit here, and this is kind of a busy page, but I'll explain it as we move through it. And what our mission is to find the voltage, current, and power dissipated by, in this case, what we're calling a load resistor 4K. So we're going to revisit this, only next time we're going to take a look at this guy, which has a little bit of a different flavor to it. So the steps on this is to remove the resistor of interest. In this case, this would be this resistor. We simply take him out of the circuit. And then this is the circle we end up with, which you can see has every single component in it except the load resistance. Now, what we're trying to do here is find VTH. That's the Thevenin equivalent voltage that's going to be feeding this circuit. So VTH is going to be representative of how these resistors and the source are affected. So obviously it'll be a lower voltage. Okay, so the first thing we have to note when we do this, and this is really kind of straightforward here, is that when we remove the load, the current flow through the 1K resistor is zero. There's no place for the current to go. So the voltage drop across the 1K resistance is equal to I times R, and 0 times 1K is going to be 0 volts. Now I said the word drop. If a component has a voltage drop of 0 volts, means that the voltage is the same on both sides of the resistor. And that's critical to understand that. So effectively, when I find the voltage at this point, VTH, or sometimes it's called VOC for V open circuit, I don't even have to take this guy into account. So that's kind of nice because it simply breaks this down into a series circuit with two resistors. And then this is what we want to do here. The overall objective of this is to find VTH and the equivalent Thevenin resistance, which represents these three resistors. And then what we have is a simple circuit where the load is connected to VTH in series with RTH. And then we just use voltage divider to figure things out. So that's what our mission is to get to this point and simplify this circuit. So again, I've drawn this VOL, or VOC rather, equals VTH. And we want to find the open circuit voltage, V Thevenin. And what we can see here is, since this resistor doesn't play into it, all I have is a voltage divider with 2K and 3K. And working that through, and here's the equation to do that, is I end up with 6 volts appearing across this without the load resistor. So that would be our VTH, and next what we want to do is find out what our R Thevenin is, the equivalent circuit of this guy. And what we have to do on that is to look into this network. So before we can do that, what we have to take into account is how we handle the sources. It's always wrong to take an ohm meter and check a circuit with the supply active. Always wrong. The ohm meter has its own source, and it generates its own current, and then the internal electronics turn that into resistance. If you got an external voltage or current source, well, it isn't going to work. So for a voltage source, and this is a perfect voltage source, and I guess you can think about a car battery fully charged. It has an internal resistance, but it is very, very low. Therein the danger lies in our car battery that's fully charged, is it contains an awful lot of chemical energy and can deliver an awful lot of current short circuit. So the internal resistance of a perfect voltage source is 0 ohms. The internal resistance of a current source approaches infinity. I'm going to say infinity. It looks like an open circuit. Memorize that. Voltage source 0, current source infinite. Now, current sources are a little bit difficult to understand because we just don't go to the store and buy a current source. We buy a battery, which is a voltage source. But they're incredibly important, especially when you get into analysis techniques. So before we go on here, let's graph a perfect voltage source. And I'm only going to do this in quadrant 1 here. So we have voltage along the x-axis and current along the y-axis, and what we know of the perfect voltage source, say 10 volts in this case, is it's a line that's vertical. And what we know about vertical lines from the standpoint of slope, that is rise over run, is it's undefined. So if you take any voltage 2, say V2, and subtract it V1, divided by its corresponding current, I2 minus I1, would be the way you'd get the slope of this line here. So if we look at this, what we could say, instead of using V2 minus V1, is delta V. And in the denominator, instead of using I2 minus I1, we could say delta I. So in this case, what we see is delta V is 0. It's 10 volts. 10 minus 10 is 0. And delta I can be anything. But it's a real number. It's a real number. It's a non-zero number. So when we do that, we end up with 0 over delta I, and that equals 0 ohms. So that's kind of showing this from the standpoint of a graph as to how we get that. Now this is just backup material to help reinforce this concept. Now let's look at a current source. In this case, again, quadrant 1, we have V along the x-axis and I along the y-axis, and the slope of a current source is 0, which means that no matter what voltage you put across a current source, the current is always going to be what it is, which in our case here, for forthcoming examples, is going to be 2 milliamperes. So the graph of this would be, again, a straight line, and that's the symbol for our current source there. And again, using rise over 1, run delta V over delta I. And what we can see here is we certainly can have a delta V. Any 2 points on this line would be delta V, but the delta I remains constant. So you'd have some value, and from that would be subtracted the same value, which gives 0. And that would be, if we took the limit of this, undefined, and in our case, we're going to look at that as an open circuit. We can consider it to be an infinite amount of ohms, infinite resistance. Learn this. Okay, so we know what VTH is, and now we need to find RTH. So what the rules say for this here is you replace the internal resistance of the source with its equivalent resistance. In the case of a voltage source, this is going to be 0 ohms. And I show this with a little link here. I've unplugged the voltage source, replaced it with its internal resistance, which is 0 ohms, and RTH is looking into this. So if I redraw the circuit to make it a little clearer, what we see is we have 2K in parallel with 3K, and that combination is in series with 1K. So working out the math for that, RTH would be equal to 2K, and there's the in parallel with 3K, plus 1K, and then we have product over sum here, plus 1K, and what that gives us is 2.2 K ohms. Now we can redraw the circuit using our VTH and RTH. So we're going to substitute 6 volts for VTH and 2.2 K for RTH. Reinsert our 4K load resistor and put him back in there. There we go. And now it's just a series circuit. Just apply voltage divider here. So the voltage across the load resistor, the 4K, would be equal to Vn, which is VTH, times the load resistor divided by the total resistance. No surprises there. Here you can see that expanded, end up with 6 volts, and then the ratio of what is in the parentheses is 0.645, and then working that out, we end up with the voltage across our load resistor. Our 4K resistor is 3.87 volts. So we found one of our 3 objectives here. Next, we need to find the current flow through that. Simple case of Ohm's law, 3.87 volts across it divided by 4K gives us 968 microamperes, or 0.968 milliamperes. This is the preferred way of saying it because it does not have a leading zero. And then for the power across this, we have three power formulas, and I can use any one I want right now. So what I've chosen is V squared over R, and that resistor is dissipating 3.74 milliwatts. So now let's take a look at the same problem, only we're going to pull this resistor out. So what we want to do is find the voltage across the 2K, the current through the 2K, and the power of the just being dissipated by the 2K resistor. So same steps. Remove 2K from the circuit, and what I have here is A and B. Everything else is in place. And what I can see here is that if I remove the 2K resistor, I don't have a current path into these resistors. And I've indicated that by I equals 0, I equals 0, I equals 0. Now what we can say about that is that zero current everywhere times a resistance is going to give us a voltage drop of 0 volts. Now what that means is the voltage at point B is 0 volts. No current flowing in this guy, 0 volts here. Likewise, let's find out what the voltage at point A is, and what we see is that, well, 10 volt battery is grounded here and simply 10 volts. So if we want to find out what VTH is, since we removed the resistor as in step 1, it's simply going to be equal to VTH equals VAB, V sub AB, and that's a doubly subscripted variable. And we're going to break that down into, make this a little clear here, V sub A minus V sub B, that's the way you decompose a doubly subscripted variable. 10 volts minus 0 volts, so VTH equals 10 volts. Straightforward. Now what we have to find is the Thevenin equivalent resistance. And this is super important here. You don't look into this network, you look into this point. Now, and this problem is going to be the same. Some problems will not be the same. So, if you remove the resistor here, RTH is looking in from that standpoint. So, once again, I followed the rules. I replaced my voltage source with its internal resistance, which is 0 ohms. And then what I can see from that is, what I have is RTH, therefore, since this is grounded, is going to be equal to 3K in parallel with 1K plus 4K. And if I wanted to, I could short this guy out. I could redraw that if I need to make it clear that the 1K and the 4K are in series, and then these two resistors are in parallel with the 3K. So there's the general equation, RTH equals 3K in parallel with, and then I parenthesize this to show that we have to add that before we do the mathematics to compute the parallel resistance. Well, 1K plus 4K is easy, 5K, 3K in parallel with 5K, and here we have product over sum. RTH ends up being, 1.875K. So we have everything we need now to solve this circuit using Thevenin's equivalent circuit. So, here's our circuit redrawn. VTH equals 10 volts. And usually it's going to be less than this, but in this particular example it's 10 volts, and it's one of the reasons why I did that. We're replacing our combination of three resistors with our Thevenin, which is our 1.875. Circuit topology remains the same. And then to find the voltage drop across the 2K resistors, straightforward voltage divider, 10 volts, which is our VTH, times 2K divided by the total resistance, 2K plus RTH, that'd be this guy here, and this is VTH, ends up being 5.16 volts. So, once we know that, finding the rest of the circuit parameters is straightforward. Current through the 2K is simply going to be equal to the voltage across the 2K divided by 2K. 5.16 is the voltage drop across the 2K resistor, and that gives us 2.58 milliamperes. Finding the power, then I got a whole bunch of options. V squared over R, V times I squared R, got the data for all of them. So what I chose in this example, first case I used V squared over R, is I squared times R, and that comes out to be 13.32 milliwatt. Now remember, this is in milliamperes, so be careful when you square that. Don't guess on units on that case. Actually put it in your calculator as 2.58 e to the negative 3, or 0.00258, and then square that. Alright, the last example is using a current source, and what we want to do now is find the voltage, current, and power across our 6K resistor in this case. I can call him R sub L, and do note that this is a different value from the previous example. And as it turned out, and I just picked these values at random, is that if I use 4K, the internal resistance of this is 4K, and it becomes a problem which you can solve in your head like that without even doing any mathematics, and that's not what I want to have happen. So our first step is to remove the 4K from the circuit, and this is what we see when we do that. Again, since the current flow through the 1K resistor is going to be 0 ohms, we have a 0 volt drop across the 1K, meaning that the voltage at point A and point B are identical. Now finding VTH in this particular example doesn't bias a lot, but I'm going to do it anyway. So we have the 0 volt drop here. Now all we have to do is figure out, and this is the simplified circuit here of this, and all I need to do is find the voltage at point A. That's straightforward. 2 milliamperes times 3K, going to give us 6 volts. So that's not too exciting. And next step, of course, is to find RTH. And this is where things become a little bit different. So I remove my resistor as I did before, and RTH is looking into the circuit. Now since we have a current source here, its internal resistance is infinite. It's an open circuit. So what we can see by that is the only thing we have here is 1K in a series with 3K, and the 2K here is not even in the circuit because of the opened here, and our internal resistance is going to be 1K plus 3K, which is 4K ohms. So putting everything together, this is what we have: 2 milliamperes, and here we have our RTH of 4K, and then over here is our load resistance of 6K, and we're going to be using the current divider rule to figure this out. So first we're going to use the general current divider equation to solve our problem here, and this is going to be the total resistance divided by the total current times the total resistance divided by the current through the 6K resistor. And the total resistance in a parallel circuit is always less than the lowest resistor. So the calculation for that is right here, 4K in parallel with 6K, and that's going to give us 2.4K. Then populating our equation here, we get 2.4K in the numerator divided by 6K, and that gives us 0.8 milliamperes, better expressed as 800 microamperes. Let's do the calculation again, only we'll use the simplified form of current divider, which is 2 resistors. Again, I6K is equal to I total. Now in this you have to be careful, because in the numerator is the other resistor. In the voltage divider, it's the resistor. In current divider, it's the other resistor, and that's going to be the 4K guy. So that's an important step not to forget. And then that's divided by R total again, gives us 0.8 milliamperes or 800 microamperes, same as we had before. So finding the voltage drop across the 6K is going to be equal to the current times 6K. 800 microamperes times 6K gives us 4.8 volts. And then finally the power, and this time I've used V squared over R, 4.8 squared divided by 6K is 3.84 milliwatts. So important part to note on this, and this is what I did with the current source, is open circuit when you do Thevenin, voltage source is short circuit. for the internal resistance of a voltage and current source. Now, I always hated having to learn things I didn't know what good it was, so let's take a look at this in application. And you don't need to know this, only we're going to be concerned with this guy. This is a voltage amplifier, and what we're going to say is we have some audio signal coming in, perhaps from a microphone, and we want to increase the level of that, and we have that same voltage going out, and this is going to be AC. So this is our transistor symbol here, and this is being supplied by 12 volts, and then off to the right I showed that as a battery. So what I want to do is size this resistor, size the capacitor, but before I can do that, I have to know the Rin of the transistor circuit. And then whatever that resistance is, I make the opposition to current flow here 1/10 or less. And if I don't do this correctly, the base frequencies will be missing from the audio, and not a good thing. So the only thing I'm going to concern myself here with is the bias network is these two resistors, and this is 100k ohms, series with 10k, and then the internal resistance of the transistors for a different course. But it's a start. Basically there's three resistances in parallel here, 10k, 100k, and that of the transistor. So just looking at the bias network here, these two resistors, is I've simplified this by getting rid of the transistor, and this is what I see here. And then redrawing this from the standpoint of Thevenizing the circuit, is the top of the 100k gets connected to ground. Why? Because it's connected to a voltage source. What's the internal resistance of a voltage source? 0 ohms. Redrawing the circuit for clarity, and I don't have to do this, but I just did it. I have 10k now in parallel with 100k, and solving that does what I get is 9.09k for the net resistance of these two resistors in the bias network. Then my last step on this, which we're not going to do, is take this resistor in parallel with the input resistance of the transistor. So this is kind of like a built-in RTH of Thevenin, but it does show a practical application for why we need to do this. Important thing is you've got to realize when you see a circuit like this, 12 volts here is 0 volts from the standpoint of the internal resistance of the battery, and what we would say here from the standpoint of AC circuits is this is an AC ground. Well, that'll conclude, and thank you for watching.